Okay, so we are starting lecture number, let me see, 35 of E503. So we are starting with the previous example. Well, this is the example in lecture number 30, and we are continuing with this example. Okay, so in lecture number 30, we have this joint distribution of x and y, where we have uniform distribution over this shaded area with the value of 1/2 and 0 elsewhere. Okay. Now the question was in lecture number 30, given x, what is the minimum mean square error estimator? And we have derived this minimum mean square estimator, so it's a nonlinear estimator, as you may remember, 1/2 signum of sine of x. Okay. So please remember that this is nothing but expected value of y given random variable x is equal to x. Okay. So this is called what we call conditional mean. Okay, that is it. Now what else? We have also calculated the minimum MSE as for this estimator, which is, let me write it over here, y minus yhat MMSE parenthesis square. Let me use this. Also as 1/12. Okay, we also had such a result. Okay, so here is the estimator, MMSE estimator, 1/2 times sine of x. Okay, that is the estimate for y, given I have observed x only. Okay, now today we will be starting with this. Let's derive linear MMSE estimator for the same problem and compare results. Okay, so let me see. So let me discuss the following. Let's say that my observation vector is, this is 1 and x. Okay. Well, I have said linear, but let me say not linear, but affine. Okay. I think it will be clear. So my goal is producing this, let's say, affine estimator, which is equal to W affine transpose times this x vector. Okay. So W is a linear combination weight, and I'm processing this linear combination weights with the observation vector this, and this will be my estimate. So what kind of processing is this? So W affine is first element, let me write it like this, 1 times 1 plus W affine, its second element, times x will be our estimate. So this is not linear because there is a constant term over here, because for linearity there should be a straight line passing through this origin without this term. Okay, so this is an affine estimator because of that. Affine estimator, as we have studied before. So what are the optimal weights? So we have studied this, the optimal weights, minimizing this. In the earlier lectures. So to minimize this, so what do we need? We need to have such a relation. Rx, let me see, W affine is equal to, my desired random variable is y. I should calculate that. So what is that one? This equation system. So this is equal to expected value of x transpose, and this one is equal to expected value of x and the desired random variable. Okay, so if I write this, so what do I have? I have this matrix times WA's first element, WA's second element is equal to a vector. Okay, So let me find the elements of this matrix. So what is this x vector? So this is 1 and x. Okay. So how about this transpose 1 and x? Okay. So what do I have over here? So I have expected value of 1 times 1. Or this is just 1x, 1x. Expected value of 1 times x. Expected value of x times 1. X times 1. Expected value of x square. So I have expected value of, over here, 1x and y. Expected value of y. Expected value of x and y. Okay. Let me write it a little better. Expected value of y and expected value of x and y over here. Okay, so to do this calculation, what do I need? I need what we call these moment information. So let me write this over here, but I won't be driving this because this is, you know, for this part I need the expected value of x times y. This is nothing but, you know, integral over this area, this density. Okay, so this is equal to, it's very easy to derive, so I'm not doing this because it will be distracting us from the main point. Okay, so it's something like that. I'm deriving this for an arbitrary power of x to the power k. For k odd, I have such a result. For k even, I have such a result. Expected value of x to the power k. Because as you see, I have x to the power x to the power 2 over here, for example. This is also equal to 0, 1, k odd, k even. So I'll be using these results, expectation results. Okay. So how do I derive those expectation results? From this density, by integrating. Especially this one is very easy, because this is just random variable x. So what is the marginal distribution of x? You can immediately see x is uniformly distributed in -1 to 1. So it's 0 mean. So when k is equal to 1, 0. For k is equal to 2, I have, oh, this is not correct, sorry. 1 over k plus 1. Okay. So when k is equal to 2, I have x square. So this is delta square over 12. So 4 over 12, 1 over 3. Okay, it seems to be correct, okay? At least for these two cases. Okay, then let me write my results. So this part is equal to 1. Expected value of x. This is equal to 0. This is equal to 0. Expected value of x square. So this is equal to 1 over 3. Expected value of y. Wow. That is also equal to, well, this is k to the power 0. That is equal to 0. This is, let me write it over here, 0. Okay. Expected value of x times y. This is when k is equal to 1. This is 1 over 4. Let me write it over here, 1 over 4. So what is the solution of this? So you see the first WA vector is 1 times something is equal to 0. So this is 0. So 1 over 3 times something is equal to 1 over 4. Then this is equal to 3 over 4. Okay. Then my affine estimator is, so it's 0 times 1 plus, second, 3 over 4 times x. But this is, remember, an affine estimator. So I have allowed this constant factor, but the coefficient of this constant factor turned out to be 0. Okay, then let me calculate the MSE. So the mean square error of affine estimator. Okay, so it is this value. So this is expected value of y minus affine of this parentheses square. But please remember we have some, okay, let me write it like this, expected value of formulas for this one also, which is equal to this WA transpose times RXY. Okay. Expected value of y square. Expected value of y square is, that's also uniformly distributed. Because of, the same argument for x, it's also valid for y. So I have 1 over 3 over here. Okay. K is equal to 2, 1 over 3, minus, now I have what? 3 over 4 times, this is 3 over 4, inner product of this vector with this vector, times 1 over 4. Okay. So what do I have? This is 16 minus 3, 13. 16 minus 9, this is 7 divided by 48. Okay. Okay. So this is approximately equal to 0.1458. Okay. I have something like that. So how about this? 1 over 12. This is approximately equal to, actually this is exactly equal to 0.083 bar. Okay. So as you see, this is the best estimator in the family of all nonlinear functions, including affine functions. If I fix my consideration to the affine functions, this is the error that I will get. And as you see, this is much smaller than that. Okay. So this is like 8, you may say, percent. This is like 14.5% of a unit. Okay. So let me also sketch this, estimator also over here. So this is, let me go over here because this is up to 1. Let's say this is minus 1. Then this is equal to 1/2, 3 over 4. This is something like that. So this slope is okay. I have something like that. So this is y affine estimator. Affine of x. Okay. With the slope 3 over 4. So this is this thing. I'm trying to sketch that estimator as you see. So what is the error of that? Let me record this. So let me make a table. So mean MSE. So this is the error, 0.083 bar. Affine estimator MSE. This is 14? 14. It's approximately 0.1458. Okay. So I have something like that. Okay. So, well, that is the performance of, you may say, the linear estimator or affine estimator. Now here's an idea. So how about doing this? Let me erase this. So about this. Now, since we are constructing parametric estimators, with optimized parameters. So what do I mean by that? W vector, weight vector. Okay. We can also take the following as the observation vector and apply the formalism for optimal parameter, let's say finding. So what do I mean by this? Now let me say that this x vector is equal to, let me define my x vector like this, 1 x square, x cube. Actually, I have only a single variable as observation, which is x. So this minimum MSE estimator is mapping, processing this by this signum function times 1/2. So this estimator is processing it by multiplying this x by 3/4. Even though I had allowed that a bias, that bias term turned out to be 0. Now you can say that now this x vector contains 4 terms. I can, if you wish, call this x1. This is x4 observation, x2, x3. Okay. So I have, as before, artificially generating some observations. So what's the purpose of that? Now, if I calculate, let's say, this estimator, well, this is quartic 4th power estimator of x vector. So what do I have? Oh, this is cubic, sorry. I have seen this cubic estimator. Then we will be having something like this. There's a weight, W1 for cubic, let's say, times 1, W2 of cubic weight times x, W3 of this cubic weight, or let me say 0, 1, 2, and 3 for this cubic weights x cube. Okay, so this looks like a cubic, isn't it? Not a linear, not an affine, cubic estimator. Because it's a cubic polynomial, 3rd degree polynomial in x. Okay, so what's the purpose of this? If I can adjust the coefficients of this, maybe I'll be getting a closer approximation to the signum function. So can I still work my way through this problem? In other words, can I find these optimal coefficients for this such that MSE is minimized? Okay. Actually, it is the same. So the only difference is I can even keep this equation. So I'm erasing this part. So this x vector is just longer. Okay. Now you may wonder, whether I'll be getting the same thing, a different result or not, but clearly you see that this is a different estimator. This is a nonlinear estimator. It's very much different from the straight line. Okay. Okay. So if I write this, now again I have this time 4 unknowns. W cubic estimator. This is 2, this cubic estimator unknowns. So I should do the same thing, isn't it? So this is 1, this is x, this is x squared, this is x cube, this vector. 1, x squared, x cube. So 1 times 1, expected value is 1. Expected value of x, 0. Then I have expected value of x squared, 1/3. This is 0. Okay. So let me, where is my, okay. Let me write this matrix from my notes, but as you see, x times 1, expected value is x squared, 1 over 3. This is okay. How about this? Again, 1x squared times x cubed, and this is multiplied by y, and I take the expected value. 1 times y, expected value, x is equal to 0, so this is 0. Okay. X times y, this is equal to 1 over 4. This is equal to 1 over 6. X cubed times y, when k is equal to 3. So this is when k is equal to 3. So this is 4, 8. This is, okay, this is 8. So I should find the solution of this. So how can I solve this? Well, if you check this and that, you know, first equation and second equation, sorry, first equation and the third equation. So what we see that I have, you know, only two variables interacting in the first and the third equation. So can you see that this, for the cubic case, again, this is equal to 0. Okay. So what do I mean by that? Set these two is equal to 0. Then this column is multiplied by 0, this column is multiplied by 0, so you get an equality for the first and the third equation. Then, well, again, no surprises, we get these, you know, even coefficients, even index coefficients of this even functions as 0, because, you know, the optimal function is an odd function, somehow I'm trying to approximate it. So it turns out that approximation does not contain, this approximation does not contain any even functions. Okay, their coefficients are equal to 0, as you see. How about the rest? For the rest, I can look at, you know, the other two equations. So in this red part, as you see, these coefficients. So if you focus on this red part, so I have again 2 by 2 equation system. So let me write that just, you know, for clarity. 1 over 3, 1 over 5, 1 over 5, 1 over 7, cubic 1, and this is cubic third power coefficient is equal to 1 over 4, 1 over 8. Okay, I have that. Now, if you solve for that, what do you get? So we get, let me see, the linear one, or let me write it over here, the solution. So this is equal to 0, so let me write with green. So these are the green ones. This is equal to 0, this is equal to 0. So how about the red ones? Okay, the red ones, the linear term is 45 over 32, and this one is minus 35 over 32. Okay, so I can get the coefficients of the cubic estimator like that. You know, again, using this. It wasn't very much difficult, isn't it? So what I have done is I have artificially generated some other random variables. But these random variables, of course, their expectation, this part, contains more information about this joint distribution. So higher order moments. Okay? So if I use those higher order moments, then I get maybe hopefully a better estimator. So what is the MSE of this estimator? So if you calculate the MSE of this estimator, so what will be our result? So let me erase this. So mean MSE of cubic estimator So remember, we had expected value of y square minus w cubic, what's my notation, w cubic transpose times this vector. This is my Rx, Ryx vector. Okay. So this is 45 over 32. This is minus 35 over 32. And there are some zeros. I'm not writing those zero terms. 1 over 4, 1 over 8. And if you calculate this, this is equal to 1 over 3, as before. So this is equal to, let me see, this is 91 over 256 times 3. Okay, something like that, a strange number. Okay, but this is again approximately equal to, let me see, 0.1185. Okay, so now I have a new term for the cubic estimator. .1185. Okay, so I have achieved something like that. So what kind of function is this? If you check this cubic estimator, so this is an odd function. I'm just making this up a little bit, something like this. Okay, so this is cubic estimator. Well, as you can imagine, I can add many powers to this. I can have another term over here, x. Well, as you can imagine, I can have the 4th power and the 5th power. But if you do this extension, you will see that all of these even indexes again will equal to 0. Okay. So for the 5th order case, this is what's called the 5th order estimator, let's say. For the 5th order estimator MSE, I get 0.1075. Okay. Well, I can repeat this. So how can I repeat this one? Now, this matrix will be, this vector will be a little bit longer. This vector will be a little bit longer. This will be a little bit longer. Then this matrix will be a little bit larger because it will be having, it will be a 6 by 6 matrix. Okay. It will be a little bit more larger. So this vector will be longer, but you do the same calculation. So what we see is that now this, simple signum-based function have this error, and if I increase my, let's say, estimator order from the 1st order to the higher orders, I'm getting smaller and smaller errors, but as you see, I cannot even reach, this one. There's still a large gap between those estimators. So the reason is, well, you can see that this signum function is a discontinuous function. Okay, so I'm always allowing a continuous function over here. So at the end, if I have, higher order polynomial, you see something like this maybe, hopefully. Okay, something like that. Okay. So in Matlab, I have actually checked what's going on. So let me show you the results. So I'm planning to have, let me show this to the camera. Okay. So if you see this, this is the estimators that I'm trying to sketch on the board. Okay. So higher order estimators are the ones approaching towards this optimal estimator, 1 over 2 signum x line. Okay. So you see MSE estimator is this one. And this is the linear estimator or affine estimator. And let's see the errors. So this is the minimum estimator MSE. This is 1 over 12, 0.08 something. Okay. So this is the 1st order estimator MSE, 3rd order estimator MSE. So you see a decrease, but there is still a large gap. So if you think about this, so if I have, as you see, some information about this density among all nonlinear functions, continuous, discontinuous, any functions that you can think of. So this is the best estimator, okay? And we have found this by simply calculating this conditional mean. So this is the importance of this. It looks like a very innocent result, but as you can see, I'm trying to complicate, I'm trying to increase my degrees of freedom by defining cubic, fifth order, seventh order estimators and so on, but even though this parametric polynomial estimator is improving its error, so I know that it will never reach this because this function cannot be approximated by a polynomial like that, okay? So I find this rather easily by this conditional expectation. So in many problems, we are using this, basically the linear MMSE. Okay. If there is a mean issue, then of course we use this affine estimators. Means, I can add always this constant term over here. Okay, that's all I would like to say. And this is lecture number 35, I guess. I will be also giving you a mini lecture. This time it will be using Matlab. On Matlab we will be, I'll be showing you how to generate those figures that I have shown on my tablet computer. Okay. So we will be having more discussions about those estimators in our Matlab session, let's say. Okay. I'll be also recording it. Very good. So that is one of the things that I would like to say. Now let's continue. Let's continue with properties of linear MMSE estimators. Okay. Number one, geometric, in brackets, vector space interpretation. So what we know, so X is our observation vector, x1 to xn. So this is our observation vector. So as I have said, I can artificially generate, something to the power third power and so on. But this is the nth element of this observation vector. So y is desired random variable. Okay. Now, what we have seen is y hat w transpose x is linear MMSE estimator, provided that, so what do we have? Provided that expected value of y minus y hat x is equal to 0. Please remember, this is what we call orthogonality relation. Okay, orthogonality. So this is our error, estimation error. So this is equal to all 0 and by one vector. So this is the estimation error of linear optimal estimator. Okay. Of course, this condition is equivalent to, please remember, Rx W times R Yx. Okay. This is equivalent to that. Previously, we have derived this, and a few minutes ago we have used this in this calculation. But let me write this properly. R, X, and Y. Okay. Very good. Now, I would like to discuss the following. Now, let's assume that what we are doing is as follows. These are my, let me say these are my abstract basis vectors. Okay, let's think about these random variables as vector. These are abstract basis vectors. So what about this one? This one is another vector, which is a linear combination of these basis vectors. Okay. So would you agree that if I sketch something like this in an abstract sense, okay, so I have some vectors over here, x1, xn, x2. So let me represent those. Actually, these are random variables, but this is just abstract drawing. So what about this? This is the span of, let's say, basis vectors. But as I have said, these basis vectors are actually my random variables. Okay, elements of this observation vector. So y hat, so this is where y hat is element of this span. Okay. So that shows us that. Okay. So by linearly combining these, basis vectors, I can get that. Now the issue is this. There's another desired random variable. Desired random variable is, let me have this blue. Well, desired random variable is over here. So it's another vector. Actually, it's a random variable, as I have said. So if you check this, now I am looking for a y hat in this span. So a linear combination of my random variables such that this is orthogonal to, so this is my E, y minus y hat. This is this, y minus y hat. So this error random variable becomes error, you may say, vector in this abstract space. Okay. So what do I have? Error is orthogonal to x1. Error is orthogonal to x2 and orthogonal to xn. Okay. So this picture and this, expectations and with this orthogonality definition, they exactly match each other. Okay. So actually, this is the reason that we call this, equality. A random variable times another random variable, when they are equal to 0, we call two random variables as orthogonal. Okay. Because the reason is, we are interpreting this calculation as an inner product, okay? We can also interpret as an inner product. So all of our previous knowledge about least square estimation now is applicable. So only difference is that I'm defining my inner product like that, and of course this becomes this is the norm induced by inner product. So all of our earlier knowledge of least square estimation now applies. So what I see is that the error, let me say random variable. Error random variable should be orthogonal to all observations. So error random variable, if you think about this like a random variable right now, is orthogonal to this. All observations means it's orthogonal to the linear combination of those observations, arbitrary linear combination. Okay, so what is my goal? My goal is minimizing this, error norm square, meaning that I'm trying to minimize the square of this estimation error. Okay, so exactly the same picture. So how about this? Now this Rx matrix is something like that, isn't it? Expected value of x1 square, expected value of x1, x2, x1, xn. So do you remember we were calling this the Gremlin matrix? or the matrix of inner products, because I can write this one in terms of inner products like that, x2, x1. This is x2, x2, if I wish. So this is x2, xn, where this is like that, okay? Then this one, for example, becomes, in terms of this notation, x1, xn, okay? So this is what we call this matrix of inner products, okay? So this is exactly the same. Now on this side of this equation system, for the linear equation system, I have A transpose A, matrix of inner products, and that is Rx matrix, as you see, with this interpretation. So this is extremely important for our purposes, because this gives us a picture in our mind, okay? So for the orthogonality, when these random variables are combined, I get this. So what is this? This is W transpose times X, okay? X vector, blue vector, and this is my Y hat, and these are the optimal W's, okay? This is, right, let me write bigger. This is W transpose optimal times X, and this is equal to my Y hat, okay? That blue point is that, a linear combination of that. Okay, so this is our geometric interpretation, and this is the reason that we call two random variables, as you see, orthogonal when their product's expectation is equal to 0, okay? So all of our geometric intuition can be transferred over here. So what else? Now, let me have a second result. So multiple, let's say, variable estimation, multiple random variable estimation from X vector. Okay. Now the issue is this, I'm again given this X vector with n elements. Okay, now the goal is, I want to minimize this, meaning that this is the estimation error for y1. y1 is just a random variable, okay? I want to minimize it. So what is the optimal w1 weights for this? Well, actually I know this very well, because this is rx times, this is w1 vector times, then this is equal to rx and y. Okay, I have this. But let me even work with the complex case. Okay, magnitude square. Now this is Hermitian. Okay, so again this is valid. No problems with this. Now let's say that there is a second vector, expected value of, not a vector, but I have said it wrongly. There is a second random variable y2 that I'm interested in. So this is second linear combination weights, processing this. So about this one, now there is a second equation system. This is x, and this is y1. I have this, okay? So let me define what this is. This is expected value of x times, this is y1 conjugate. This is expected value of x vector times y2 conjugate, and this is expected value of x Hermitian, which is the same. Both of them are the same. Okay, that is it. Now, if I can find these two optimal, W1 and W2, I am done. I can estimate optimally Y1 and optimally Y2 in terms of linear mean square error. Okay. So this will be the optimal estimate for Y1, optimal estimate for Y2, provided that I select my weights according to this. Now how about this? Well, instead of doing so, would you agree that I get the same result? So this is Rx matrix, W1, W2. Then let me write this as Rx Y1, Rx Y2. Okay. So this is nothing but, the first equation is first column of this left-hand side, first column. So first column of the right-hand side is this. So if you compare the first column of both sides, it is this equation. If you compare the other column, you get the other equation. Okay. So then let me call this W matrix, as this becomes my W matrix. Okay. Now you can say that the following. Then I can estimate this y vector, which is y1 hat, y2 hat, as, okay, W1 Hermitian, W2 Hermitian, because this is our definition, W1 Hermitian, W2 Hermitian of X, am I right? Okay. Or I can write this as W matrix Hermitian. Okay. So as you see, if I'm interested in multiple variables, so let's say that I'm interested in 2 variables, so desired vector this time. Okay, desired vector is something like that. If I'm interested in 2 of them, of course, what kind of error measure should I define? Let me define this problem properly. So, expected value of y minus y hat, this, okay, where y hat is wx, okay, a linear combination of x elements of x, is nothing but in this case y1, y hat 1, y2, y hat 2 norm square, which is y1, y1 hat norm square plus y2, y2 at norm square. Okay. So we call this the total MSE. The reason is this is the sum of MSE for, let's say, y1 and y1 hat and y2 hat estimators. Okay. So this is the sum of that. So if I define my problem like this, minimize this total MSE using this W1 vector and W2 vector, okay? Minimize this MSE. So total MSE is minimized by W1 and W2 vectors if I write, for example, if I define this W matrix as W1, W2, if we define something like that, and Rx of W is equal to this, okay? Rx y1, Rx y2. But how about this? If I define my x is like as this one, x y Hermitian. Okay. So this is y1 conjugate. This is y2 conjugate. So this is also then equal to rxw times rxy. Okay, according to this. So this is some extra information, let's say. So if I satisfy this equation for W matrix, then I'm done. Then the optimal estimator, y vector is W Hermitian times x, is the optimal estimator. Optimal estimator minimizing total MSE. So this looks like a new result a little bit, but actually there is nothing new. This is the reason that I have explained it as you see over here, because I'm selecting W independent of W1, independent of W2. So I'm doing my best to minimize this error by W1. Then I'm doing my best to minimize this error by W2. And of course, these, individually, this and this is minimized. Then their sum is minimized. Okay? So this is the repetition of the same problem, let's say 2 times. Okay? For different desired vectors. And problem is essentially decoupled, as you see. Okay? This is the reason that I can write that. So what is nice about this? Now, there's again a single equation. And this single equation, what we see is, this equation provides a minimization of this. So this is minimizes this is my total MSE. So this is minimized by, as you see over here, okay, where this is a linear estimator. Y hat is equal to W Hermitian times x. Now, let me do this. Okay, let me write y hat over here. So W Hermitian times x, isn't it? W Hermitian times x, where W will be, W matrix this time will be Rx inverse Rxy, what is this? Hermitian times x, okay? So I have something like that. So if you check this, this is Rxy Hermitian, Rx inverse Hermitian, but this is already a Hermitian symmetric matrix. So its Hermitian is, again, Hermitian does not play any role, times x. So how about this? If I take, this will be my final result, yx, Rx inverse times x. Okay, that will be the estimator. Well, that is the case. So if I check this, so maybe we need to explain this a little bit, but this is very simple because this is this part. If you take the Hermitian of this, now you have y times x Hermitian. So y times x Hermitian is the definition of this vector. Okay. And by the way, this makes a lot of sense. Why? Because I have this x vector coming in. This x vector is somehow, it's processed by this Rx matrix. Then x vector is, the result is further processed by Rxy vector, and I get y. Okay, so maybe from these indices, subscripts, you can follow, what is going on if you want to remember it that way. Okay, so this is essentially decorrelating the elements of this x vector, this operation. And then from this decorrelation result, I am estimating, for using the relation between x and y, I am estimating this y. Okay. That is the result for the, this is valid for, as I have said, complex case. So this is a general result. So what else do I have? Well, the important case is this. Let me have an example for this. So let's say that my observation vector is, this is a very important example. Okay, so this is my observation vector. So this is my desired vector. This is noise vector. And this is, let's say, what we call the channel. This is known channel. Okay, H matrix essentially. Okay. So the goal is, of course, noise and desired vector, we assume they're uncorrelated. Okay. Then I want to estimate yhat. Well, find linear minimum mean square estimator for yhat. Okay. I'll be just writing this actually. So let me erase this part. So I'm estimating a vector. So what should I do? Solution. So let me write this. I need to find this Rx matrix. So Rx matrix is expected value of x times x Hermitian. Complex case. Then I have H, Ry, H Hermitian for this term. Then I have Rn for the second term. Okay? Because there will be n times n Hermitian over here. There will be a cross term, but because of their uncorrelated, and all of these quantities are zero mean. Okay, we don't worry about mean. As I have said, we can add the mean later on and so on. Okay, Rx. So let's assume they're all zero mean. So Rx is this. So how about this? Ryx. I want to implement this. Expected value of. So this is y. So I need this x Hermitian over here. So this is then hy plus n Hermitian, right? So how about this? This is y Hermitian. Then I have Ry. I have h Hermitian over here. And y and x, y and n, they're uncorrelated. Y and Hermitian is all zero. Uncorrelated and zero mean. I have that. So what happens? The final estimator is yhat. Now I'm writing this. Ryx, Rx inverse of x, which is inverse times x. We are done. Okay. So this is what we call inverses over here. This is, let me see, what we call linear MMSE estimator for vector y. Okay. So as I have said, you may think that estimation of the vector is more complicated than the other case, but actually we are estimating each element of the vector individually with this complicated looking result. That is the result. But once I can write compactly this final result, we are done. And admittedly, this result is very easy to remember. Am I right? Okay. So you can easily apply this. Okay. So what else? So let me write something and then we will have a mini break. So this is number 2. Okay. So I have number 3. So this is our third observation. Let's say that linear combination of observations, that is m times x, as a new observation vector. So I will explain this title a little bit better, but let's assume that I have this x vector, x1, xn. Now somebody comes and says that, well, I would prefer to have a linear combination of this x vector by an arbitrary matrix M. Okay? So, meaning that I am transforming this x vector to another x vector. So this is an invertible, let's say, matrix for now. It may not be invertible, but let's say that it's an invertible for now. So this is like a lossless transformation. Now the question is, if I process my result with this xm, do I get a different estimator or not? That will be our topic. So we will continue from this topic after this break.